சரி ஸ்டார்ட் பண்ணிடலாம். நீங்க சொல்லுங்க.
Good afternoon, everybody. It gives me an immense pleasure to extend you a very warm welcome on behalf of Department of Civil Engineering, New Prince Shri Bhavani College of Engineering and Technology for the webinar on seismic resistant design of tall building. Now I request Dr. Karthik, HOD, Department of Civil, to deliver the welcome address and resource person profile.
Good afternoon, everybody. It gives me immense pleasure to give the welcome address for this webinar on seismic resistant design of tall buildings by Dr. S. Senthil Selvan, Professor of Civil Engineering, SRM Institute of Science and Technology, Kattankudattur. I welcome you, sir. Thank you for accepting our invitation. Next, I would like to welcome our chairman, Mr. Loganathan, vice chairman, Mr. Naveen Prasad, director, Mr. Swaminathan, principal, Dr. Saravanan, our civil department faculty, heads of other departments and faculty from other departments. A warm welcome to you all. Now, I will give a brief history about the resource person. Dr. Senthil Selvan is presently Professor of Civil Engineering, SRM Institute of Science and Technology, Kattankudattur. He completed his DCE from Muthaya Polytechnic College, BE Civil and Structural Engineering from Annamalai University with University first rank. He qualified in GATE and completed his ME in Structural Engineering from Government College of Technology, Convener. He obtained his doctorate degree in Structural Engineering from Anna University, Chennai. He has 23 years of teaching experience, out of which 3 years as principal of a Anna University affiliated engineering college. He has 7 years of industrial experience and has published 15 Scopus Index papers. He has also attended national and international conferences. He also serves as approved research supervisor in Satyabama, Wales University and Shankara University. He is at present guiding 15 PhD scholars, out of which 2 scholars have successfully completed their PhD. He has also funded projects in Madras to his credit. He is also serving as reviewer in national and international journals. In addition, he is a life member of ISTE and a fellow of Institution of Engineers India. Thank you.
Thank you, sir. It's my great honor to invite our resource person, Dr. S. Senthil Selvan, Professor, SRM Institute of Science and Technology, Chennai, for his intellectual words.
Thank you, madam.
Thank you.
Is it screen shared, madam? Hello? Hello?
Yes.
Sir, it's visible. It's visible.
Visible. Okay.
It's visible, sir.
Okay. Good afternoon, everybody. I thank Dr. Karthik, HOD Civil of Shri Bhavani, New Shri Bhavani Engineering College, College of Technology, for giving this opportunity and inviting me to talk about the topic is seismic resistant design of tall buildings. I also thank the coordinator, Mr. Adlin, and I thank all the management people of the college for giving me this opportunity to share my knowledge, whatever I gained. The topic is seismic resistant design of tall buildings. Here, I will give the overall view about the tall buildings first. Then, what are the precautions or steps to be taken during the construction activity of tall buildings to take care of earthquake forces. These two things is the overall presentation point that I'm going to give to you. First, we will talk about the tall buildings, and then we will see the briefly the details of the measures to be taken during the construction of tall building to take care of the seismic forces. Now, this is the title page. You can see here. This is a tall building. Okay, how can you see that this is a tall building? For to understand it is a tall building for the audience. Uh, I I show one photograph of an aeroplane flying across the building. That shows the building height is nearly it is almost in the level of flight the height of the flying plate height up to this that level the building reached. So it comes under, or we can say it is a tall building. So the tall buildings are very much essential in this context or in this scenario to take care of a large amount of economic and other points to be taken into account for the particular country. Now we will see one tall building. Here, tall buildings are structural systems which should be economical to resist internal forces due to wind uh, or earthquake forces. Tall buildings are a structural system which should be economical to resist lateral forces due to wind or earthquake forces. See, whenever we are seeing the ordinary residential building, we are not considering about the lateral forces. So when the lateral forces are predominantly considered, we can say it is a tall building. So in the tall building, when you are happen to decide it should be taking care of the lateral forces due to wind and also earthquake forces. That is, these two forces are considered to be very important in the design of tall building. Lateral forces acting on it should be within the prescribed criteria for strength, drift, and comfort of the occupants. Actually, the lateral forces acting on the tall building should be within the permissible limit. Or, in other way, I can explain, the tall building should be designed to considering the to take care of the lateral forces. Drift is the nothing but the ratio between the lateral deformation, the top by height of the building. This also within the permissible limit. When the building is very strong, and when there is a lateral displacement is less, the drift will be less. So accordingly, we have to design the building to take care of the lateral forces in the prescribed criteria, considering the strength, drift, and comfort of the occupants. Comfort of the occupants is ordinary in the normal building. The people living in the normal residential building having the height of less than 50 meters, they are very comfortable. That means there is no lateral movement on the building. But when you are considering the tall building, the possibility of a small amount of sway will be occurred in the tall building that makes the people uncomfortable. So you have to design the tall building to make the people comfortable. That is a very important thing to be remembered. The civil engineers while designing or while looking into the tall building. The first modern multi-story building constructed using steel skeleton and Chicago in 1883. That's the first multi-story building in the. We can say that it was the multi-story building concept was started in the year 1883 itself. Then various towers across using steel skeleton and reinforced concrete structures have come in America in late 30s, and in the period of 1920 to 1930, many excellent structures are coming into the in the world. Particularly, we can say in that during that period, the world wonders, one of the world wonder, Empire State Building comes in the US in the 1929. That was considered being one of the world wonder during that time. We can say that the types of tall building according to the height or according to the number of floors, we can differentiate the tall building. When the building higher than 50 meter are termed as tall building, and buildings higher than 100 meter, okay, they are termed as skyscrapers. So between 51 to 99 meter, we can say it's a tall building. When it crosses 99, we can say it's a skyscraper. Buildings 300 meters or higher are termed as super tall building. This is another type. When the height of the building is taller than 600 meters, it is termed as a mega tall building. Therefore, the tall buildings are differentiated by 4 ways: tall building, skyscraper, super tall building, and a mega tall building. Why we have to go for tall building? Before going to see the seismic design of tall building, we will see what about tall building and how to construct, or how to take care of the points to be remembered while constructing a tall building. Taking care of the lateral forces like earthquake forces and wind force. So the tall building demand for tall building comes due to the scarcity of land. Scarcity of land in the sense, when the urbanization comes, the population increases, but the area is same. So to accommodate more population in smaller area, it is mandatory to go for high-rise building to accommodate more people in smaller area. That's the first demand, scarcity of land. Second one, economic growth. Economic growth is nothing but the growth of the particular place. When you consider the Chennai city, the economic growth depends upon the population movement, and more amount of corporate building comes into the in the city. So when more amount of buildings are required for in a smaller area, ultimately you have to go for tall building. That's economic growth. Increasing demand for business and residential space. When it is becoming a metropolitan city, the lot of business should be taken care for the particular area. The area is remains same, but more amount of corporate people will come and go, and more amount of building is required in a lesser space. That leads to bringing the tall building concept. Technological advancement in earlier, when you consider the 1960s, we used to calculate the forces and moments in any building, which may be a small residential building of ground plus 3 or ground plus 10. We are going during the time when the computer was not invented. We are going for calculating the forces, axial forces on beams, bending moment on beams, axial forces on column, shear forces on column. All the forces will be designed manually using moment distribution method, cornice rotation method, the substrate frame method. Lot of methods are available in earlier days. By doing manual calculation, we have to calculate all the forces coming to the structural components. So then we have to go for design. But when there is invention of computer and the invention of many softwares, so technological development increases, that leads to very easily we can design the tall building, the components of the tall building very easily, accurately, and economically. So innovations innovation is a necessity of invention is a necessity of actually the necessity is the mother of invention. Actually, when we want to know some new thing, the necessity comes into picture. So whenever we want to some new material, necessity comes, and the necessity is the mother of invention. So whenever we go for tall buildings, a technological advancement is if it is possible to go for a very good technological invention, then it is very easy to go for designing a multi-story building very easily. And cultural significance and the prestige. Actually, the cultural significance is nothing but that is the status of the particular place. Cultural significance, and it is a pride. We can say that this is the if you're taking a Burj Khalifa in Dubai, it's a pride to Dubai. That is the world tallest building is in our country, and that's a pride. That is one of the significance of the tall building. Human aspiration to build higher. Actually, the human aspiration, usually the desire, we can say, the desire of the people, human being, is invented, or the desire of the people to go for tall building is the human aspiration. That is the demand for making for tall buildings. Need for tall buildings is a mark of prestige civilization, landmark in the global picture. Global picture means if you're taking Google Earth, if you take Taj Mahal, that is a landmark of our India. Similarly, the tall buildings is the landmark of the particular country. It is also one of the pride, symbol of pride. Okay, increase in demand for shelter is met without encroaching the agriculture land. When we are constructing a multi-story building or tall building, we are using only small area, and we are not going for encroaching the area which is already they are using for the agriculture purpose. We are not going to encroach the particular land. That is one of the advantage and need for tall, and it leads to tall building. History of tall building, the world's first skyscraper is a home insurance building constructed in Chicago in the year 1883. This is the photograph of the home insurance building constructed in Chicago in 1883. This was the first during the time first skyscraper. And some of the other towers comes after the Chicago Tower. Is one of the John Hancock Tower, AN Tower, and one Mark Tower. These are the towers comes after the this Chicago Home Insurance Building and comes under skyscraper. Design philosophy of the design of a tall building through a thorough knowledge of high-rise structural components and their modes of behavior are essential for a lateral load system. If you want to design a building, tall building, you should know the the behavior of the structural components and the modes of failure and how it was behaved. All the things are required before going for design a tall building. It should be efficient and economic. Whenever you are going for a tall building, or you are going to design a tall building, or you want to go to construct a tall building, it should be efficient and it should be economic. So we are the civil engineer. We always see these two things very effectively. One is efficient and it should be economic, and it should serve the purpose also. That's another thing that we have to follow in the design of tall building. Increase in availability of structural analysis program needs to understand the fundamental knowledge of structural behavior. See, whenever there is different types of softwares are developed for the analysis of tall building and the design of tall building, and it is availability of structural analysis program leads to the fundamental knowledge of structural behavior of all structural elements in the tall buildings. These are some of the loads that act on the tall building. Usually, we know many loads already we know. It is general loads, dead load, live load, wind load. These are some of the general loads. Beyond which, some loads are very, very predominant, or peculiar, or is special for the tall buildings. They are impact load, and wind load, and blast load, and seismic loads, that's earthquake load. These are very, very important loads to be considered in tall building. In earlier, before the impact of flight on World Trade Center, the impact load is not considered in the design. Okay, they will consider the impact load not that a huge amount of impact load was not considered in the earlier design of tall building. After the impact of or the collapse of World Trade Center by the impact of plane, they considered while designing the tall building. They are now being considered the impacted also while analysis type or while designing the multi-story building structural components. And the wind load, always it is acting laterally, normal to the structure, and blast load. You see, after that, this blast load already we have code books available. We have to consider the blast load. Uh, it is a short time load, short duration load that also we consider while designing the tall building. And always we know the earthquake force. It's a predominant load that will create a lot of problem for the particularly for tall building. When the building is a very small, ordinary building, when it is a height is less than 50 meter, earthquake forces will not create that much impact on the building. But because of the height, because of the height of the multi-story building or tall building, the earthquake forces will create a large amount of lateral displacement and sway or deformation from bottom to top. It may you can see the displacement at the bottom is very minimum, and compared to the top, it is like a pendulum. Or if you can say it is a fixed at bottom, free at the top, like a cantilever. The oscillation will be there. Okay, therefore, this is the during the seismic earthquake load, a large amount of force will be developed at the bottom due to the base excitation of the ground action. The lateral forces develop a large amount of deformation of the building. That also we have to consider while doing the design of the tall building. Classification of tall building, structural system of tall building can be divided into interior structure and exterior structure. Actually, the tall building concept is not like the regular building. Okay, there are two types of concept: interior structure and exterior structure. Interior, and this depends upon the position of the column and the core of the column, and then it is like a column, how the columns and beams are provided in the tall building. When you're taking the interior structures, by clustering steel columns and beams in the core, engineers create a steel backbone that resists tremendous wind forces in the inner core. You can, if you say taking the interior structures, a large amount of columns are provided in the interior, and all the slabs are extended from the interior. Okay, this is the interior structures, where the exterior structures is a new skyscraper, the CS7 Chicago. Like it is an example for CS7 Chicago. The engineers move the column and beams, the core to the perimeter of the building, and rigid. It's act as a tube. That's a tube-like structure. And if interior structure and exterior structure commonly, sometimes they will come together. It is called a tube-and-tube structure also. Tube-and-tube, that's the interior and exterior. So here, the exterior structures are where the columns are provided at the periphery of the perimeter of the building, creating a hollow, rigid tube as strong as the core design, but it is weighing much less when compared with the interior structures. Sometimes the interior structures are maybe it may be a shear wall. Okay, when taking the previous this interior structures, we can make the shear wall concept here. Shear wall is nothing but a wall constructed from bottom to top using the reinforced concrete without any disturbance, or that it won't stop at the middle portion. It will start from bottom to top. It is provided for the earthquake point of view that we will discuss later detailing about the shear wall. Is a shear wall is a vertical element seismic force resisting system that is designed to resist in-plane lateral forces, typically wind and seismic load. This is the inner core of the shear wall, like interior surface. Outrigger system. Interior structures, we have outrigger structures. Here you can see the inner core. The red color is the inner core, and the outrigger is the outer core is here. Green color is outer core. Red color is inner core, and it is connected with systems called outrigger system. Outriggers are rigid horizontal structures. Outriggers are rigid horizontal structures designed to improve the building overturning stiffness and strength by connecting the building core or spine distant columns in the perimeter. The inner core is connected to the perimeter by the outrigger system. Example is a Shanghai World Financial Center, where the inner core is connected to the outer core by the outrigger system. This is the photograph I showed. Exterior structures, tube and tube. Already I told you tube system, outer tube. This outer, this exterior structure, and many kind of exterior structures are available in like a tube system. These are some of the tube system available, and these tube systems are incorporated in the building in and around the world. Okay. And exterior structures, coming to the exterior structures, this is a diagrid system. Diagonal grid. We can make it as like this diagonal grid. Diagrid system is adopted in tall buildings due to its structural efficiency, flexibility, and architecturally planning. Compared to closely spaced vertical columns in frame tube, diagrid structures consist of inclined columns. You can see that in the photograph. There is an inclined column like a basic, a diagonal, you can say the diagonal column. It's a consists of inclined column on the exterior surface of building. It is provided like the diagonal systems are provided to take care of a large amount of lateral forces. This is a very, very effective planning, effective structural point of view. It is very, very effective to take care of the lateral forces. Exterior structures is a another one is a super frame where it's composed of mega columns comprising braced frames, large dimensions at the building corners provided. When you're taking the super frame, in the corners are very, very effectively placed. Mega columns are provided comprising the braced frames. Our columns are connected with the bracings, that's called braced frames, so that the entire structure will be a mega strong building. Comes under the top concept. The space stress structures are modified braced tubes with diagonals connecting the exterior to interior building. Actually, the space stresses are three-dimensional, where the exterior diagonal members are connected to the interior members using the horizontal thing. This is that's why it is called as space stresses. That induce that they make the structure more strong, or you can say it is more reliable, and it is with earthquake point of view or lateral load point of view, it will take a large amount of lateral forces without any drift. I will give some example for tall buildings. Petronas Tower. It is when the Burj Khalifa was not constructed, the Petronas Tower became the world's tallest tower, and it was constructed. It is in Kuala Lumpur, the capital of Malaysia. This is the one of the example of like a twin tower connected with a common platform at this story level. The Petronas structural system is a tube and tube system. That means outer tube and inner tube will be there. Applying a tube structure for external wall buildings is a common phenomenon. Already explained what is a tube and tube wall. It is a exterior surface are made with large amount of number of columns in the perimeter of the building. The Petronas tower is having 88 floor towers are constructed largely of reinforced concrete, and you can see the outer packet. You can see the glass packet. This glass packet are designed because it is a religious, a Muslim religious country, designated resembles the motifs found in Islamic art, a reflection of Malaysians Muslim religion. It was constructed taking into consideration of this their religious part also. Architecturally, the height of the Petronas tower is differentiated with the following points. Architectural point height is 451.9 meter, and the tip means it has some small mosque, or you can say it's a tower is extended to the top to provide the the signal lights to provide some transmitters. That's the tip of the tower is 451.9 meter, and the top roof is 378.6 meter. It is situated at 378.6 meter, and top floor is provided 375 meter. Totally, it is having 88 floor, and total height is 451.9 meter. When it comes to the world tallest tower, Burj Khalifa is a tallest building. It was now it is in Dubai. It is the tallest building, 828 meter height. The height is 828 meter long from the bottom to top. It broke all the world records of the tall building, and designed by Adlin Smith. The Burj Khalifa resembles a village tower situated in US, and a central hexagonal core with the three lobes. It is a central hexagonal core with the three lobes are provided. You can see here. This is central hexagon with the three lobes are provided. One wing at each tire sits back. That means each wing is when it is going up or it is moving in the top direction, bottom to top. Some of the tire is sits back or it stops at level, so that it will go the cross section area going getting on reduced from bottom to top. Upward spiraling pattern, let me say, decreases the cross section of the tower when it's from the bottom to top. Y-shaped plan providing high performance. This is why we are providing Y-shape. Like we used to say in our traditional chair, we have four-legged chair, we have three-legged, and that is called Mukali. This have three legs only. And like this, it have three legs, so it have sufficiently strong, and it put its legs on three sides, and it resists all types of loads. Upward spiraling reduces wind force system, central core torsional resistance, and a corridor wall extends the central core to the wing seal. Usually, I told for a central core, all the corridors are extended from the central core. I will explain through this diagram also for your better understanding. The central core, from the central core, in the central core, all the corridors are extending from the central core. This is the example of the Burj Khalifa interior structures. Extend central core to the wings end. This is the foundation diagram of the Burj Khalifa. Construction started 21 September 2004, and superstructure supports a large amount of oxy raft. Design is based on geotechnical aspects, and it was designed and soil was tested properly. And according to the geotechnical engineer, the foundation was decided, and it was based on the geotechnical report. The foundation was laid 3.7 meter thick raft. Four separate posts. Actually, 3.7 meter thick raft should not be laid at a stretch. It should be laid in a layer by layer, and four separate posts are used. And we have 192 piles with the capacity of taking care of the load of 3,000 tons. When come to the construction stage of the Burj Khalifa, it was started in February 2007. First, it surpasses the Sears Towers. When it comes to the level, it surpasses the height of the Sears Tower. Then 13th May, a vertical concrete pumping was started. It was the first vertical concrete pumping for the particular height. Is 141, level 141 is a very, very the floor is height is very very long, and it is possible by the people to pour concrete by vertical concrete pumping technology. 12th September 2007, World Freestanding Structures. Now it is the 12th September. It surpasses all the height of the building available in all over the world. The 1st September, tallest main structures was constructed, and 17th January 2009, it was inaugurated. It reaches the height of 828 meter, became the world's tallest tower. November 2008, how it was construction is going on here. Here now May 2007, March 2008. You can see here the cross-sectional areas going on getting reduced so that it have the large amount of stability, like spiraling. You can say the spiraling effect. And 2009 it was inaugurated. Height comparison, consider starts with Great Pyramid in Gaza and the Eiffel Tower, Empire State Building, Twin Tower, Taipei 101, and World Trade Center, no more available, CN Tower in Toronto, and radio mass provided in Gabon, and the world tallest tower, that's Burj Khalifa, that was constructed in Dubai, 828 meters. So now it is the tallest tower, and the things are, we can say, the every tallest tower will become a second. If it is constructed, if another building was constructed, the height more than this one, so every tower will become lost its fame when another building was constructed, a tall building constructed more than this height. It is possible in 2030. Is it possible? Someone will make going for constructing a 1 mile height building. That's 1.6 kilometer height of the building. It is also possible in 2030. That's the first mile high building. So they can say that's a 1 mile high building. It is also possible in future. Actually, I told the tall buildings are found to be more flexible than low-rise building during the earthquake shaking. And whenever the earthquake comes into the picture, we have to consider the shaking of the building, and we have to design the flexibility is one of the main criteria while doing the design of tall building. Now coming to our topic, seismic resistant design of tall buildings. Basis of earthquake. First, what is earthquake? How it will occur? The earthquake is nothing but ground motion. How long it will occur? How strong? What is the frequency content? How long, how strong frequency content is differentiate the nature of earthquake. And how long? It is in seconds. How strong? That depends upon the strength, or so it depends upon the magnitude of earthquake. Frequency content. How the frequency will be? What will be the frequency? Or frequency means nothing but a ground excitation or a ground acceleration. That's called frequency. How the building will respond for the earthquake forces? Strong vibrations will create during the earthquake. Large stresses and strains will be developed in all the structural components. I repeat once again, when the ground motion occurs, a large amount of stresses and strains will be developed in the structures, particularly the structural components, like starts from the foundation to the top floor. All the building components will be subjected to large amount of stresses and strains. And while designing a tall building to consider the earthquake forces, we have to consider this amount of large stresses and strains that will occur in its lifetime. And accordingly, we have to design the structural components, like all the structural components, like starts from beam, column, slab, and everything. And that may be local failure. Sometimes when the earthquake force is heavy, that local failure maybe leads to collapse of the structure. It may be it may not be a sudden collapse, because when it gives sufficient time, that is called progressive collapse. Collapse will not occur suddenly. When we design the building to take care of the earthquake forces, the collapse of the structure will not be a sudden collapse, and it will be a progressive collapse. So we have we have large amount of time so that the occupants may be moved to a safer place. So that is it is during the strong earthquake. Okay, that may occur very occasionally. Basic design concepts. I told already in this webinar we are going to detailedly discuss about the various design concepts while designing a tall building under the seismic force. always I told soft story. In earlier, when you consider a tall building, usually they left the ground floor for car parking. That means there is no wall, there is no, that's open. Car will be parked on the ground floor. That means that is called soft story. The weight of the particular story is very less when compared with the weight of all the story above that floor. I repeat once again, soft story is nothing but the weight of the particular story, because there is nothing is available. No, there is no wall, there is no window, there is no floor, nothing is available. There is no movement of man-made material, nothing is there. Only it is open space where the weight is very less, where compared with the weight of the building above the ground floor is very large, so that it acts as a pendulum. It acts as the entire mass is concentrated on the ground floor, and it may be possibilities that some lateral displacement will occur, and a failure will take place. Therefore, avoid soft story, because during the earthquake, the top floor, the ground from the ground floor, top of the ground floor, the entire building starts oscillating, and the bottom ground floor is like a fixed one, whereas the top level is oscillating, and it breaks the, or it collapses the ground story columns and beams very easily. Therefore, avoid the soft story concept. This is the deformation of soft story during the earthquake force. You can see the left side. This is the earthquake force. Earthquake forces are applied, and when the earthquake force applied, the bottom the ground level movement of the ground level is takes place. Floor level takes place, and the entire building above the ground floor starts as moving in all the directions. The bottom ground story will act as a pendulum, and it leads to collapse of the entire structure. So therefore, avoid the soft story. And also, don't provide a soft story in the middle of the floor. Also, avoid the soft story upper floors. So maintain uniformity through the height, and provide. If you are going to construct a shear wall, if the shear wall is considered here, it was break at this level. Okay, then the shear wall concept disconnects at this point. Okay, therefore, it is very important to take into consideration of the soft story, or avoid soft story in the upper floor also. Bracings are the bracings are provided in the columns. Actually, the bracings are provided for redistribution of moments, particularly when the seismic forces or lateral forces acting on the column. We take in the column when lateral load is acting on the column, a large amount of moments will be created in the particular column, and it tends to move in a lateral direction. And during that case, if it is provided with this kind of bracings, it transfers the load, excess load, to the other column through the bracing. That is the action of bracing, action of bracers. Therefore, the bracings are provided symmetrically. Then only it will serve the purpose. This is the building a top view. Here the bracings are provided non-symmetrically. Only 1, 2, 3 bracings are provided. It is unsymmetrical. Here bracings are provided in symmetrical bracing. When the load is acting, lateral load is acting, what will happen to the building when it was provided with a non-symmetrical bracing, when it was provided with symmetrical bracing, the next slide. Here, when it's non-symmetrical bracing, when lateral load is acting on the floor, on the building, it tends to rotate due to the unsymmetrical action of the bracing. When it was a symmetrical bracing, there won't be any topple, or it won't rotate. It will take care of all the amount of forces, or we can say the bracing is provided, and the bracing will provide serve the purpose, that we can say. This is the symmetrical bracing, that it will move, it won't rotate. Okay, therefore if we are allowing the lateral movement, but you are not allowing the rotational movement or torsional movement. This is the discontinuity stiffness and resistance. If you want to provide the building vertically, if you want to filling the or if you can take a infill. Yeah, infill means providing the brickwork or any other method to construct between the column. It should be continuously you have to construct. If you are providing the pillar material in unsymmetrical manner, it causes discontinuity and the discontinuity and the stiffness also not properly distributed, and it leads to collapse of the structure when during the large amount of earthquake force. Provide cylinder. We are discussing about the design concepts of providing cylinder structural walls. Structural walls along principal direction be symmetrical as possible. When you provide a cylinder structural walls, that will be in a normally a rigid wall will behave. It is like a brittle material. If it is a cylinder wall, it like a brittle is ductile material. It will sway very predominantly, and it will take a large amount of lateral forces without any collapse of the structure. Avoid short column. In building, sometimes it is necessarily happens to provide short column. These short columns are very critical in shear failure, because the short columns are already it is a failure is by crushing, and the shear is very critical failure in short column. Avoid short columns in the tall building. And this is a very important concept. Strong column and weak beam theory. There are two things available: strong column, weak beam, or weak column, strong beam. Okay, actually, considering the column is weak, beam is strong. Consider when load is applied, then when column is weak, beam is strong. Many number of beams are connected to the column. So when column is weak, the failure will be the collapse of the beam leads to collapse of the large amount of the beam columns connected to the particular large of the beams connected to the particular column. So when a column failure means nothing, only the column will not fail. Whatever the beams connected to the column will also get failed. So this concept should be eradicated by making the another concept a strong column and weak beam. When load is subject to a large amount of beam forces acting on the beam, that transmit, we can say that will that kind of beam will fail. That the failure is a local failure. Only that beam will fail, and it is possible to rehabilitate the beam very immediately, and so the structure will not fail. When the column fails, structure will fail. When the only one beam fails, structure will not fail because it is a local failure. When column fails means it is a global failure. That is very important. That's a strong column and weak beam theory. And we have to provide dampers. We will see the different types of dampers in the later slides, especially what is the damper and what is the use of purpose of dampers. Effects of earthquake on buildings. You can see the effects of earthquake in the many building here. This is a failure of the column, failure of the packets, and the failure of the this is soft story failure. You can see here. And this is the failure of the column in the ground floor level. These are some of the failures due to the earthquake on the building. Taking a case study, Hotel Matsushita Sheraton Carabellada Peninsula. Here, we can taking the hotel building during the earthquake of in 1967 Carcass earthquake. 10-story building was taken. The building consists of reinforced concrete frame with shear walls in the transverse direction. So it's 4 to 8. And the shear wall is considered only from 4 to 8 up to the floor level of 4. There's no shear wall, and due to that large amount of failure occurs up to 4th floor in the building. The shear walls are interrupted the 4th floor level, where there were 1.1 meter diameter reinforced concrete columns which were severely damaged due to the non-availability of shear wall. The exterior walls are constructed of tiles. Note that there was some damage to the tiles walls also. That will not take into consideration of the earthquake forces. Details of structure of slide showing damage of 1 meter diameter column third story. Here, because the shear wall is not, started only from the fourth story, the third floor, due to the earthquake, the concrete column was collapsed, or you can say it's cracked or developed in an inclined manner. These columns are longitudinally reinforced with 34 to 40 mm scoop bars with 12 mm circular ties spaced at 150 mm center. 34 to 40 mm bars are provided, even though it was cracked due to the non-availability of shear wall. The shear wall is taking care of large amount of earthquake forces. That's why that's the main point of providing the shear wall. The tiles provided in the column where the concrete was shattered. Due to this providing tiles, due to the crack developed, the tiles were shattered from the column. During uh, uh, the load on the column or during the earthquake forces, the column will buckle. There are two types of buckling. Two types of mode shapes are available in the buckling of the column. One is a first order, the second one is second order. First order is a single dimension. That's the only buckle will take place in a vertical direction. And the second order buckle will take place not only the vertical direction but also along with the rotation. That is a torsion. Therefore, in the first diagram we can see here it is a first order mode, failure mode of the column. Here you can see here the black color, that is a it is a buckle. It is parallelly it also rotate. That's the second order buckling of the column during the seismic response of the building. Steps in seismic design. Here, plan the building structure as in symmetrical way, both in plan and horizontal. See, it is not. Sometimes it is not possible. Symmetrically, because availability of the land is a very important criteria. If it is a coarse land, it is not possible to make one symmetrical. But as far as possible, make the plan symmetrical. The structure is symmetrical so that it is very safe in the earthquake point of view. Avoid open ground soft story. Already told you. Avoid soft story. That is open ground floor. Avoid weak story and provides a strong diaphragm. That's the thinner slabs and flat slabs are to be avoided. Thinner slabs and flat slabs are to be avoided because it is vulnerable to earthquake point of view. Providing openings of doors and windows at distance of minimum 0.6 meter from the column edges. When you want to provide doors and window frames, it should be a minimum 2 feet away from the column face of the column. Do not add appendages like water tanks and swimming pools, etc., which will create a vast difference in the center, because all the center of masses should be coincide with the center of the building. Whenever we're providing some masses away from the center of the building, like providing swimming pools or water tanks away from the center of the building, that will create eccentricity during the earthquake forces, and it will create a collapse. It will reach collapse of the building. You have to consider the soil profile also, or you can say the soil characteristics, whether the soil is predominant or it leads to any liquefaction. Because the soil liquefaction is a very important phenomena that should not occur for the building. Okay, during the earthquake, soil liquefaction will topple the building very easily. Okay, also while designing the building, tall buildings. For tall buildings, we have to consider the National Building Code and the Indian Standard Codes while doing the analysis, while doing the design. We have to follow the Indian Standard norms and the National Building Code norms. Select a good material, concrete, brick, steel, water maybe, and the steel should be at least minimum 14% elongation should be there. Okay, then only we can say the steel bar will take a large amount of or you can say it's a ductile nature. Then minimum yield strength 4.5 Newton per square you have to take. The yield strength should not be greater than 4.5, and if you are providing 500 Newton per square rod, check it whether it have the 14% elongation. already we know we have to provide a plinth beam, lintel through the connecting the column in a primary direction, secondary direction also, so that it will act as a bracing. It will act as a bracing in the ground level and lintel level and roof level, so that whenever there is an excess amount of moment, it will transmit the moment to the other column or beam column through the beam. Building geometry of the building should be proportional reasonably, avoid long, tall, or wide dimensions which are known to result to poor seismic performance during the earthquake. Maximum, I told already, the geometry should be symmetrical. These are really helpful in controlling the problems like a blockade of roads, collapsing of adjacent building, or unfortunate situation of building collapse during an earthquake. When it is unsymmetrical, this collapse of building it will spoil the adjacent structure also. Okay, therefore, as far as possible, the geometry is considered symmetrical for the earthquake point of view. The height to plot width ratio actually maintain the less than 1.3. For plot size, the plot size is we have to follow as per class 6.6 of National Building Code 1983 part 3, and the height of the building considered according to class 9.4.1. This plot size, when you mention considering this plot size, it is IS 1893 for the earthquake resistant design of structures, that will give a stable structures. Okay, this plot size will give, if you follow this rule, the building will safe against earthquake. IS 193 provisions are given, improve the shape and subsequently behavior of building during earthquake shaking. And design provisions may not exist explicitly with the height of the building, but desirable to ensure that building are not made too long, and the height gives a regular desired shape, and the slenderness ratio should be within the permissible limit. According to IS 193, we have to follow these norms for the tall buildings and for the earthquake forces. Under the design stages, the designer is a very important person for design of tall building, because after the analysis over, taking the vulnerable values or maximum values, we have to go for designing of the tall building. Should address the influence of the masonry infill, lateral forces, and the behavior of the structure, and either be taken into account the design process, or all the things we have to take into account. By separation gap of the column, already told you, 20 to 50 mm compared with the calculation. A weak column, strong beam design, thick slab, which diaphragm, avoid the slab, and the flat slabs should be avoided. This already we have seen. Provide cross walls which will shepherd the structures. Actually, when you are taking the soft story, there is no shear wall. There is no cross walls are available, because only the columns are available. Because when it's make it a car parking, because you can't provide any cross walls between the column. So when it's a cross walls are provided, at one point of time, when the columns are subjected to more amount of load during the earthquake, it will transfer the load to the wall. The wall will take some amount of energy, some amount of earthquake energy will be dissipated through the walls. That's why we are concentrated staying the provide as far as possible to the cross walls. Provide shear walls also in symmetrical fashion. It should be boundary, however, large level arm to resist earthquake forces. So this is a very important thing. And the seismic design data, we have to consider the IS 193, how the seismic design base shear are calculated, and this base shear is calculated using this formula taken into account while designing the structural component of the tall building. This base shear is taken into account while designing and detailing of the structural components. This is the horizontal seismic coefficient for structure. You have to calculate the horizontal seismic coefficient structure by using the formula available in IS 1893. Considering the value, and these values are calculated and incorporated in the design. After calculating the seismic design coefficient and calculating the base shear, we have to go for design for earthquake forces. Calculation base shear corresponding already calculated. Base shear is calculated. Also structure under the static lateral forces for the gravity load. Normal analysis we have to do, and we have to do the analysis of the building for the earthquake forces. Combination of gravity load, lateral load, detailing them for ductile behavior. Combination of lateral load, gravity load and the earthquake forces, and design the building and detail the building and go for ductile detailing. It will give a good structure to take into account all the forces combinedly, both gravity and lateral forces. Ductility, how to improve the ductility of the building. Ductility is the ability of structure undergo elastic deformation, large amount of deformation. Whenever you're taking the tall building, there is a large amount of deformation takes place in the top level. The drift, that is the movement of the top floor, maybe is clearly visible. That is that is you can't say when the top story of the building is moving from its place. That is not a meaning of a collapse of the structure. It is swaying. It is displacing. It is not a collapse of the structure. It is mentioned here. The ability of structure to undergo inelastic deformation beyond the initial deformation with no decrease in the load resistance. That's a very important point. That's why given in the capital letter, no decrease in the load resistance. Load will be resisted by the structure, and the flexibility makes the structure to undergo a small amount of deformation that will dissipate the energy due to the acting of the load. So it may be a gravity load or lateral load. Luckily can be increased in the section by decrease the percentage of tension shield. Whenever tension shield is decreased, the good old concept we used to teach our students, under reinforced section is preferred than over reinforced section. Steel controls the design, not concrete controls the design. That is the concept here. We have to follow the decrease the percentage of tension shield so that the steel will, concrete will not fail first, steel will fail first. It will be giving sufficient warning to the people because the steel will have large amount of ductile nature. Increase the percentage compression steel and decrease the tensile strength of the steel. Uh, uh, don't go for beyond 415. Increase the compressive strength of the concrete so that some amount of tensile nature will also increase because 0.7 square root of FCK will be tensile strength of the concrete. When the concrete strength is increased, some amount of tensile strength of the concrete also increased. So it becomes some amount of it will take some amount of tensile load also. Increase in compression flange area in flange beam. That is the compression flange is the area of the T and L beam. Increase the transverse. There's a shear reinforcement you can increase. I told that the shear walls I had to provide it from bottom to top of the building without any interruption using the reinforced concrete structure. It acts as a structure while during the earthquake forces it will absorb large amount of force. Okay, symmetric. It should be provided symmetrically as possible to design actually for 1.5 times the lateral storage shear force. It should be designed to take into account 1.5 times the lateral storage shear. In another solution is to provide a cross braces in elevation without any hindrance to vehicular movement. If it is possible, we can provide even the car parking some cross bracing without affecting the movement of the vehicle, if it is possible. Or we can go with some kind of columns, T L shaped columns can be used. That will be a symmetrical manner. But design of these columns is very important. These are some of the basic braces to be used in tall buildings. For seismic resistant design of building, we have to good detailing is required because in the tall building detailing is very important. Because detailed diagram will go to the site for the people those who are going to execute the work. Therefore, good detailing is very important. And for the detailed detailing, as per IS 13920/1993, anchorage and overlapping are to be calculated as per the code for the steel members. Okay. IS code 436/90 earthquake resistant design construction of the building is to be followed for the design and for the construction of the tall buildings. These are the design methodology adopted in IS 8183. We have to follow. I already told you. These are the resist minor earthquake or resist moderate earthquake without any significant structural damage. Minor earthquake, there should not be any damage. Moderate, there may be damage, but the structural damage is not there. Major earthquake, there may be damage, but there is not collapse of the structure. These are the main phenomena, 3 points followed by IS 1893. Construction change, good planning, good workmanship, and the construction practice is very important. We have to use good material, substance. All the materials should be tested before using, particularly for tall building. There should not be any compromise. It should be made for the tall building materials to use with the tall buildings, and provide proper cover for the concrete to avoid any falling of the concrete. Our blocks should be used. The follow design rules furnished by the good structural engineer and do not make any deviations. Compact the concrete by means of needle vibrator wherever possible to make a good concrete, high dense concrete. And curing of the concrete is very essential. Experienced supervisors should be are appointed in the construction stage. This is the last heading for the high-rise building or tall building, structural dampers. What's a damper? Dampers is like a shock absorber. It will absorb energy because when the movement of earthquake, tectonic plate will be moved and large amount of forces developed, the ground excitation will take place and the building large amount of force will be developed by the base excitation if it is absorbed by the building by some means. Absorbed by the building by some means like a shock absorber, the building will become safe. That is the concept became dampers. We can provide some kind of dampers in the building to absorb or to dissipate the earthquake energy, so the building will become safe. Mechanical system which dissipate the earthquake energy into specialized devices which deform yield during the earthquake. They enhance the energy dissipation. These dampers enhance the energy dissipation or it will absorb the large amount of energy they installed so that the structure will resist a lesser amount of earthquake forces. The structure will not, no forces will be transmitted to the structure. All the forces of the earthquake forces will be absorbed by the dampers. That is the advantage of providing the dampers. Structural dampers are critical parameter for structures that are subjected to dynamic loading. That is, dampers are subject to dynamic loading developed by the seismic forces. Structural dampers are implemented in building to deal with the dynamic excitation. Dampers are efficient in the sense that they dampen the energy input due to dynamic loading through various mechanisms. These mechanisms are we are going to see. The sources of vibration effects on the structure due to the earthquake, mechanical and human sources, wind. This will develop lateral forces, or we can say develop a dynamic motion on the building. Due to earthquake, the seismic waves caused by an earthquake will make buildings sway and oscillate in various ways depending on the frequency and direction of the ground motion. According to the ground motion, excitation, the building will oscillate. The seismic activity can cause excessive oscillation on the building, which may lead to structural failure. To avoid structural failure, if the amount of energy developed by the excitation will be absorbed by some means, the structure will become safe. Okay, that is the advantage of providing dampers. Mechanical and human sources. Some of the mechanical human sources will develop the extra energy. Most of the people, many people moving and making a union can cause a serious problem in large structures like a stadium, structures like damping. Whenever the stadium is there, we have to provide dampers, or else the movement of people at a short period will create a lot of lateral movement. That should be avoided by providing dampers. Vibration caused by heavy industrial machinery, generators provided in the building, and to avoid that the buildings, this dynamic loading should not be delivered to the building by providing dampers. Large ocean-going vessels like ships may employ the tune mass dampers to isolate the vessels from its engine vibration. The engine vibration will not go to the ship. By providing dampers, the vibration will be not given to the ship. That is one kind of dampers that provided in the ship. Due to wind, the force of wind against tall buildings can cause the top of the skyscrapers to move more than a meter. You can see here in the Burj Khalifa, as we have seen, there is a movement of top floor by 1 meter. That's a movement of top floor is 1 meter left to right, right to left. That is allowed because flexibility is a very important phenomena, and the people who are living in that particular floor are experiencing this one, and they are familiar with, they are trained for that displacement. The motion can be in the form of swaying or twisting, depends upon the direction of the wind and the height of the floor that takes place. And that you can see here, due to the wind, the building will behave in a lateral movement, like a lateral movement. And this is the buildings and the use of the structural dampers, the area. Different types of structural dampers and the application. Frictional dampers. This is the frictional dampers. When the two plates are moving in the opposite direction, the friction will take place. Okay, when the friction takes place, it will absorb, it will absorb more amount of force during the earthquake. During the earthquake, when it is two plates are moving in one over the other, some amount of force will be absorbed by the friction by the plates, and it will not give the force to the structure. So this is called frictional dampers. Frictional dampers are considered to be the most effective and economic solution for seismic earthquake. Yeah, in late 70s, the friction dampers were developed to inspire the principle of friction brakes in automobiles. Like in automobiles, the wheel is stopped by providing the rubber shoes that having the frictional force between the wheel and the rubber shoe. That is similarly, when the frictional force is developed during the seismic force, will absorb large amount of force by the a large amount of earthquake force was absorbed by the frictions developed by the plates provided in the structure. Nowadays, friction dampers are available for tension cross bracing, single diagonal. Many places they are providing. They consist of series of steel plates specially treated to develop most reliable friction. When the steel plates are provided, it has sufficient friction force can be developed during the earthquake, and it will absorb the earthquake forces, and it won't deliver the forces to the building. The example is here. These are some of the friction dampers provided in the building. Metallic dampers, next one. These metal dampers are popular and inexpensive, provided energy dissipation device. You can see the energy dissipation device, because during the earthquake, a large amount of energy was delivered, produced, developed. That should be absorbed by any means. Structure will become very safe. Well, as a civil engineer, we have to provide the dampers in the affected prone zone area buildings, so that the structure will become very safe. These are the other metallic damper provided, and this will give a good ductility and high potential for dissipating energy and post yield region. In the metallic damper, there are two types of dampers provide single round hole damper and the X-shaped dampers. During the earthquake, the single damper will move in a lateral direction, absorbing the energy or dissipating the energy, and it will yield. Before deformation, after deformation, you can see here. Before deformation, after the earthquake, it yields, and it will take large amount of earthquake forces, so that the building will become safe. And double X-shaped dampers are provided. Double X-shaped dampers after the earthquake, after the dissipation of energy, you can see that the X-shaped become widened, and after deformation, that shows it takes a large amount of earthquake forces. This is another X-shaped metallic plate dampers are provided in the building, where the two-story steel frame with the metallic dampers are provided. When the load is applied, large lateral forces, this damper will absorb large amount of seismic forces, so that the structure frame will become safe, in stable position. And viscoelastic dampers, it is a viscoelastic material is provided at the middle, so that when the structure is placed over this steel plant, the viscoelastic material will absorb large amount of forces, or you can say the energy developed by the seismic forces will be absorbed by the viscoelastic material, and the structures over which will become in stable position or in a good position without any damage or without any collapse. magnetic induction, it transitions to structural dampers like a structural oscillation due to the dynamic loading. This magnetic induction provided energy from dynamic loading and dissipated through electric energy. This due to the magnetic induction. The traditional structural dampers, it will develop, it will absorb the dynamic loading and make the due to the magnetic property, it is converted into electrical energy. So the electrical energy delivered or developed by the dampers will be used for some other purpose, active damping devices. Tuned dampers, we have three types of tuned dampers: tuned mass dampers, tuned liquid dampers, tuned liquid column dampers. So here, tuned mass, these are tuned dampers are provided by the it is a man-made dampers. Man-made dampers, on a tuned mass dampers are example is a very interesting topic. Tuned mass dampers. It was provided first in Taipei Tower, where it was provided in Taipei Tower, and it is height of 598 meters. Tallest building in the world at one time before the Burj Khalifa. Here at the middle portion of the building, they provided a very huge, like a steel ball. They provided this is a tuned mass provided in the middle of the building, and this will oscillate according to the oscillation of the building, against the oscillation of the building. I repeat once again. You can see here the animation of the tuned mass. The mass is situated normally in the building. You can see here in the previous slide. It is usually it is in stable position. When the building is moving in left to right, this mass will move in the right to left, so that it will absorb large amount of forces. That's why it is called, it will dissipate the energy. Okay, that's called tuned mass. You can see here now, keep in this mind, when it is moving left to right, it is moving right to left. Here, when the building is moving in left to right, it is moving in right to left, so that it is moving against the movement of the building. So it will absorb more amount of earthquake forces. When there is no earthquake forces, it will be in stable position. And when the building starts moving, it also starts moving in opposite direction, absorbing large amount of forces without giving any damage to the building. It is a tuned mass damper provided in Taipei Tower, Taipei 101. 60. It is a weight is 660 ton. It is a pinnacle type 4.1 each, which was installed in 2002. Furthermore, the tuned mass damper system were installed in many structures, such as other structures also. After that, they provided such as Bloomberg Tower, New York, Grand Canyon Skywalk in Arizona, USA, and Shenkan Bridge in Hong Kong are provided with the tuned mass dampers. This is a very interesting man-made invention. Tuned liquid column damper. Tuned liquid column dampers. Actually, a column of liquid is provided. It is like a cushion. The column of liquid is acts as a cushion. It will control the vibration of the building. Okay, that's called the tuned liquid column damper. You can see here. This liquid is provided so that when there is a movement of the building, it will move in other direction to dissipate the energy. This is the tuned liquid column damper. It was installed already in the world. It is in the height 297. It is in the Campus Center of Pennsylvania Plaza, Philadelphia, USA. They provide the tuned liquid mass damper, column damper, tuned liquid column dampers. Which is nothing but a column of liquid provided. This column of liquid will act against the movement of the building, so that it will absorb large amount of energy during the earthquake. So far we have seen the concept of tall building and seismic resistance design of tall building. The important points to be followed while doing the construction stage or planning stage, analysis stage, design stage, and construction stage. What are the important points to be considered, and what are the dampers to be required to provided to absorb the earthquake energy? And we are coming to the conclusion. Nowadays, there is an increasing trend to construct tall structures to minimize the increase in the space problems in urban areas. That's no other way. We have to go for tall buildings. That's mandatory in this situation. These structures are often made relatively light, comparatively flexible, possessing quite low damping, thus making the structure more vibration prone or away from the vibration. Various methods are there to overcome these problems, like aerodynamic design, structural design, auxiliary damping devices are we can provide so that the structure will become safe or stable in the earthquake point of view, particularly tall building. But recently, it is found that the use of dampers is the best to overcome this problem by providing. We have invented a large amount of dampers to take care of the seismic forces or dissipation of energy developed by the earthquake. That's called seismic force. We are coming to the end of this one. I thank the management, VC, Nisha, Pro VC team, HOD Civil Engineering of SRM Institute of Science and Technology for facilitating me to do this presentation. I thank my student Dr. B. Vijaya, Associate Professor Civil Engineering, India University, and Mr. R. Ram Subramanian, Assistant Professor Civil Engineering, SRM Institute of Science and Technology, for helping me in developing this presentation material. I thank everyone, and I also want to thank chairman, principal, vice chairman, director, HOD civil, and convener of this national webinar, Knowledge 4.0. And thanks each and everyone for the passion listening. And thank you one and all for the passion listening. And if any question, you can ask.
Thank you, sir. Thank you very much for sharing your profound knowledge with us. Now it is time for queries. I call upon Mr. Shekhar, Associate Professor, Department of Civil, to raise the queries which is received from participants.
Good evening to all. First of all, I thank you, sir, for your detailed explanation, and it is very informative to us.
Thank you.
Now, I would like to ask a few questions from the chat box.
Yes.
The first one is, what should be the configuration of an earthquake-resistant building?
Usually, I told as far as possible, symmetrically placed building will be subjected to very less amount of seismic forces as far as possible. Or we can go with the like a spiraling, like a Burj Khalifa. We can go with a spiral pinnacle so that it also resists a large amount of seismic forces. So that's also possible. And providing the dampers, or if it is not possible to go with symmetrical sections, we can go with asymmetrical, but the required amount of the provisions to be made to dissipate the energy during the earthquake. That's a very important concept. That's a good question.
Oh, thank you, sir.
Okay.
Another question.
Okay.
In which software commonly used to design a tall building or skyscraper?
Actually, it is ETAB is available. Particularly for tall building, ETAB is there are two versions available. ETAB is only for the academic point of view, so software ETAB is available. For the other professional point of view, they have to purchase some of the software ETAB. Usually, for the practicing engineer, going with ETAB is good. And Tekla structures are also giving some softwares. And now the Midas comes into the picture, and it is also providing some software, particularly for tall building. That depends upon the height of the tall building, height of the nature of the building, purpose of the building for which it's being constructed, and the type of the material that is going to use, whether it's concrete or steel. Accordingly, they can decide which software they can use. But usually, these are the softwares what I told will be very, very useful for them. Okay.
Thank you, sir. Now I hand over the mic to Adlin, ma'am.
Thank you, sir. Now I invite Mr. Shivakumar, Assistant Professor, Department of Civil, to give a brief history of our college.
Thank you, madam. Good evening to all. New Prince Shri Bhavani College of Engineering and Technology is an engineering institution offering the courses of UG and PG levels. This college is run by Tirumadi Abranji Ammal Educational Society, Chennai. This educational society also runs other premier institutions in Chennai. During the last 31 years of tireless service, this educational group has grown from strength to strength. NPSB CET currently enjoy the patronage of a large number of students studying in various engineering courses at PG and UG levels. NPSB CET is approved by AICTE New Delhi and affiliated to Anna University, Chennai, offering the UG courses of BE in ECE, EEE, CSE, Mechanical and Civil Engineering, and BTech courses of IT, and PG courses such as MCA and ME in Applied Electronics. The institute has prime objective of providing quality engineering education for the students studying in all engineering and technological streams and to provide an opportunity to utilize physical facilities and human resources and knowledge resources available in educational institutions to maximize the knowledge acquisitions. Thank you, sir.
Thank you, sir. Now it's time to wind up the session. I invite Ms. Subhatra, Assistant Professor, Department of Civil, to propose vote of thanks.
Good evening, everyone. So it's my proud privilege to propose the vote of thanks. On behalf of Civil Engineering, I extend my very hearty vote of thanks to our resource person, Dr. Senthil Shelvan, for sharing his experience with us today and sharing his time with us today. So you took this event to a higher level, sir. Thank you for your eloquent speech, sir. Thank you. And I extend a sincere thanks to our chairman, sir, vice chairman, sir, director, sir, principal, sir, for your vision and commitment to work and its execution. A warm thanks to our HOD, Dr. K. Karthik, and our entire civil department for organizing such an outstanding and inspirational session. And I finally thank all the participants for their active participation. We look forward to the same in the future also. Thank you so much.
Thank you, ma'am. I hope you all found this session valuable for future. Once again, I thank everyone for making the session successful. Thank you.
Thank you. Thank you, Karthik.
Thank you, sir. Thank you.
Thank you, sir.